Good evening. This is the last class of second class of the Regression. In the previous class, I discussed Darwin version test, DW test, and today I am going to discuss Darwin H test. So, Darwin H test, suppose apply OLS to the model YT beta 1 YT minus 1 beta 2 YT minus 2 beta r YT minus r plus beta r plus 1 xt1 beta k xt k minus r plus u, where u equal to rho ut minus 1 plus epsilon t v1 is OLS of beta 1 where v1 hat equal to estimator of var v1 then the Darwin H statistics is denoted by H statistics is equal to R root over n by 1 minus n per hat v1, which is asymptotically normal 0 1 and R is sum over t equal to 2 to n et minus 1 by sum over t from 2 to n et square. This test is applicable when n is large, when 1 minus n r hat b1 less than 0, then test breaks up. In such case, the following test can be adopted. Introduce a new variable epsilon t minus 1 to ut equal to rho ut plus epsilon t. Then ut equal to rho delta rho t minus 1 yt. Now apply OLS to this model and test H naught delta equal to 0 versus H1 we get like H1A, H naught A, delta not equal to 0 using P test. H naught A will accept it then H naught rho equal to 0 is accepted. If H naught A delta equal to 0 is rejected, then H naught rho equal to 0 is rejected. If H naught rho equal to 0 is rejected by DW test, it does not necessarily mean the procedure of first order autocorrelation in the disturbance procedure of first order autocorrelation in the disturbances. It could happen because of other reasons also. For example, disturbance, for example, distribution may follow higher order air process. Sorry, this is not disturbance. It says we follow higher order air process. Two, some important variable are omitted a dynamic model is specified functional term of model is incorrect. Now consider estimation procedure with autocorrelate error with autocorrelate error showing autocorrelation coefficient is known. Consider the estimation of regression coefficient under first order autocorregressive disturbance autoregressive disturbances and autocorrelation coefficient is known, the model is y equal to x beta plus u, ut equal to rho ut plus epsilon, rho ut minus 1 epsilon. And assume epsilon u equal to 0, epsilon u prime equal to psi, which is not equal to sigma square identity metric. That means EYs are correlated and expectation of epsilon equal to 0, expectation epsilon prime this is equal to sigma epsilon square. Here the OLS of beta is unbiased but not in general. Efficient and estimate of sigma square is biased. So we use generalized least square estimation procedure and generalize this least square estimate of beta denoted by beta hat GLAC, which is equal to x prime xi inverse x. We knew this thing. Okay. And xi inverse, which is of this form, if you write down the form of xi, then you can easily compute xi inverse. to the dot. Okay. So please check. This is the inverse I. That is, just check that this I inverse, this matrix is the inverse of Xi. Okay, first you write down the Xi, then you verify whether this is the inverse or not. Okay, this is your homework. We employ this proceed as follows. Find matrix P such that P prime P equal to Xi inverse. Here it is root over 1 minus rho square minus rho 1 last row is minus rho 1. Now, we have step 1, now the step 2. Transform the variable as y star py, x star px, and epsilon star p epsilon. So note that the first observation is treated differently than other observation. For the first observation, this is root over 1 minus rho square y1, root over 1 minus rho square x1 beta into 1 minus rho square u2. Whereas for other observation, yt equal to rho yt minus 1, t equal to 2, 3, 10, and this can be written as xt minus rho xt minus 1 prime beta plus ut minus rho ut minus 1, where xt is the row vector of x, also root over 1 minus rho squared ut and better to write xt prime, okay, and ut minus rho u naught u1 minus rho u naught have same property. So we expect these two errors to be uncorrelated and homoscedastic. The first x, if first column of x is a vector of ones, then first column of x star is not constant. Its first element is root over 1 minus rho square. Now apply OLS with observations y star and x star, then OLS estimator of beta, which is denoted by OLS beta hat, is equal to x star prime x star inverse x star prime y star, and dispersion of this OLS estimator is equal to sigma square x star prime x star inverse, which is equal to sigma square x prime y inverse x whole inverse. And since sigma square is unknown, so estimate of this is equal to sigma hat square x prime y inverse x whole inverse, and where sigma hat square, which is equal to y minus x beta hat prime y inverse y minus x beta hat by n minus k. And now when autocorrelation coefficient is unknown, so this case 2, then the estimator is denoted by beta hat f. That means it is a feasible GLS estimator of beta, which is equal to x prime omega hat inverse x inverse x prime omega hat inverse y. Where omega hat inverse is the y inverse matrix with rho is replaced by rho hat, and this rho hat is estimated by simple correlation coefficient, that is R, which is equal to sum over R from 2 to n et minus 1 by R from 2 to n et square, and where et equal to yt minus xt prime b, and b is OLS estimator of beta. So sometime you may use instead of R, you can use two different modification. One modification due to you can use this modification instead of this R, you can use R star n minus k by n minus 1 R. This is due to we'll estimate that, and again we may use this form instead of R, which is equal to this for large n when B is the DW statistics for H not rho equal to 0. Next is Darwin procedure. So this is the first procedure, simple correlation coefficient for estimating rho hat, and this is the second procedure for estimating rho hat. That is called Darwin procedure. In Darwin procedure, the module yt equal to yt minus rho yt minus 1, which is equal to beta naught 1 minus rho plus beta xt minus rho xt minus 1 plus epsilon t, where t equal to 2, 3 up to n, and then yt can be expressed as yt equal to beta naught star rho yt minus 1 beta xt plus beta star xt minus 1 plus epsilon t, where t equal to beta naught star, which is equal to beta naught 1 minus rho beta star, which is equal to minus rho beta. Now run regression using OLS. In model 1 and estimate R star as the estimated coefficient of yt minus 1 so another possibility is since rho belonging to -1 to 1, so search for a suitable row which has smaller error sums. There are other methods. I just mentioned the methods. If you're interested, you can go through this. I do not want to discuss this methods here. That is Cochran-Orchard procedure. This is another method for estimating rho. And the next method is Regression procedure. Or grid search procedure. So you can, if you're interested, you can go through this procedure. You can read this procedure. You can get any standard book of regression analysis. You can easily get this procedure. So please read this thing. We do not want, I do not discuss these two procedures. Okay. So, and another procedure is Paris-Winston procedure, and you may apply likelihood, maximum likelihood procedure. Okay. So please, if you're interested, please go through this. Please read this procedure. I think you know the likelihood procedure. This is a very simple thing. Just compute the likelihood function for the model. I can discuss this thing with me. Procedure. So in likelihood method, first you write the likelihood function. And denote the likelihood function by capital L. Suppose y follows normal f beta sigma epsilon square xi. The likelihood function, which is the function of beta rho sigma epsilon square. So this is equal to 1 by 2 pi sigma square n by 2 data of epsilon n by 2, because y is a n-dimensional normal distribution. xp minus 1 by 2 sigma epsilon square y minus x beta prime epsilon inverse y minus x beta. Okay. So then you compute log likelihood and you did this thing. Then partial derivative of log likelihood with respect to beta with respect to rho, then with respect to sigma epsilon square, then we get normal equations. This gives the normal equations, and but this is, you cannot solve this easily because this is a non-linear function. So the steps are first step, first write first get the anyway of sigma square, then substitute it back into likelihood function and obtain likelihood function as a function of beta and rho. Third step, maximize this likelihood with respect to beta and rho. Okay. And then you get first epsilon hat, this is equal to 1 by n y minus x beta prime epsilon xi inverse y minus x beta. This is the estimator of Emily of sigma epsilon square. Then this substitute, then we write the real star. So Ln star should be k n minus 2 ln y minus x beta prime epsilon inverse y minus x beta 1 minus rho square 1 by n, where k equal to n by 2 ln n minus n by 2. So maximization of ln star is equivalent maximization of this. These are equivalent. So this maximization is same as this maximization. So for this, for maximizing this function, we use optimization technique. Of nonlinear regression. if n is large and absolute value of rho is not so close to 1, then 1 minus rho square 1 by n minus 1 by n is negligible, and then the estimate of beta will be same as obtained by nonlinear least square estimations. So this is all. I want to stop here. So I request you to submit your assignment, otherwise before time. Before time means the last date is 31st July. Otherwise, you may penalize. You know there is a 20 marks for internal assignment. I actually internal assessment and I assess. The internal assignment is based. Internal assessment is based on only your homework or and assignment. So please submit the assignment before 31st July. Otherwise, I cannot entertain you, and you may penalize for this. Please tell your friends to submit the assignment before time. So, have you any queries and questions? Please tell me. Otherwise I stop. So this is all about your, the syllabus of your syllabus. Okay. So, have you any queries and questions? Please tell me. Otherwise, I end this time. Again, I repeat this thing. Please submit your assignment before 31st July. Otherwise, you may penalized. And all the best for your coming exam. Okay. Thank you. So, have you any queries and questions? Okay. Thank you. But after few months, that after few months, we will again continue the regression with a actually we will discuss some new topic on regression after few months. If you enjoy the process, please stay with us.